Let me start recording before I forget. All right, so we've got, after today, essentially 2 classes left, both on Mondays. So next Monday and then the Monday after Thanksgiving. Just to give you an idea of what's going to happen for the rest of the semester. Today we should probably finish 5.5. Which means on Monday, I'm going to go over 6.6. Technically, we're supposed to cover it. Some of my other classes are a bit behind and aren't going to get there. But I'm going to cover 6.6, and I'll talk about it a bit more on Monday. But that's going to be some bonus question material for you guys for your final. Because 6.6 is a bit complicated. I usually like to cover it in 2 or 3 days instead of just 1. So I'll cover what I can of it so that you've at least seen it, but then it'll only show up in bonus question material because it's a bit complicated. Because what I want to do is I want to make the Monday after Thanksgiving just a review day, so I don't want to do more material that day because your final is cumulative. So I want to take that day after Thanksgiving before your final to just be able to talk about whatever you guys want to talk about. But anyway, there's going to be one more homework assignment for the rest of the semester that's going to pop up next week. I'll probably extend it a little bit past the Monday after Thanksgiving because I'm not trying to make y'all do homework over Thanksgiving. So I'll probably extend it to the end of that week. And if anyone wants to get it done, they can get it done early next week. But anyway, so that's pretty much how the rest of the semester is going to play out. I should hopefully have your exams graded by Monday, Tuesday at the latest, hoping to get them done by Monday. And once I get them graded, I'll of course update your current grade, and I'll put up a grade calculator to, you guys can play around with that and see kind of what you would need on a final to kind of land where you want in the class. So anyway, let's go ahead and finish up these notes. So we have one last question here. This one's technically still 4.4, and then we're going to go on to 5.5. So remember in 4.4, we talked about this, it feels like forever and 2 days ago, but we were talking about this before the exams. Let me remind us what this is. So this is when we're talking about essentially the units and the interpretation of an integral. So remember, the units of an integral are the units of essentially the y values multiplied by the units of the x values. Now, technically, there's one thing that I didn't write down here that might be helpful. Where can I squeeze it in? Squeeze it in kind of in here. So remember with the interpretations of the derivative, I kind of gave you like a cookie cutter way to write it down, even if it didn't sound like great English. And there is technically a way to do that here. So let me go ahead and write that down in case people are having a hard time figuring out how to interpret it. So how do I want to phrase this? I'm going to say this always works. So if you want to interpret an integral, you can always phrase it as a change in something. I'll write that something in a second. Between A and B, where A and B are the bounds of the integral. Now you would want to include the units of A and B. So if it's like seconds between time equals 1 and time equals 3 seconds. But essentially this change in, this is the context of the integral. So say it's an integral of a velocity. Well, then velocity, the integral of a velocity gives you distance. So it would be a change in distance between A and B. That phrasing is often going to give you a very bad English sentence. If I'm honest, it's usually not going to be phrased very well. But as you guys know, with the when we were doing derivative interpretations and everything like that, I don't really care if it sounds like good English as long as it gets the point across. So if you're having a hard time figuring out how to interpret these in a way that sounds nice, you can always just kind of default to a change in something between your two bounds. All right. So let's look at this last question from 5.4 here. So we've got, sorry, I'm gonna move this thing. You can't see it, but I can see it. I need it out of my way. Can you move, please? Thank you. There we go. So we have the rate of growth of the populations of 2 species of plants, which is going to be measured in new plants per year, are shown in the figure. So we're going to assume that the populations of the 2 species are equal at time t equals 0. So I want to be very specific here. Let me give these 2 things names. Let me name this S of t. Nope, just name it S of t. And I'll name this one P of t for plants, I guess. So note that these 2 functions that are graphed are not the actual populations. They're the population growth. So essentially, if we're looking at something like, say, the integral from 0 to 1 of S of t, this is going to be, if we look at just the units would be the units of S of t, so plants per year, times the units of t, which is just years. So the integrals here that we're going to be looking at are going to give us the amount of plants, which is what we're going to be wanting to talk about, because notice in these questions it says which population. So we actually want to talk about the amount of plants, not the rate. So we're not actually looking at the y values of these functions. We're going to be considering the integrals. So say I want to know which population is larger after year 1, after 2 years. So first off, this graph always confuses me. Let me plop these down so I remember where these stop. So we have time equals 1 and time equals 2. So say I want to know which population is larger after 1 year. So the one thing to make note of is that they both start at the same amount. We don't know what that amount is, but we know that they start at the same amount. Because what these integrals are going to find us is actually a change in the population of plants. So say I was actually interpreting this one between, oops, come on, go away, year 0 and year 1. So if I'm looking at these integrals, which remember are areas, so if I'm looking at this first species, if I look at the area underneath of that function between 0 and 1, I'm going to erase this in a second, but we essentially have this area here. So whatever this area is, I don't actually care about what the number is, but whatever area is there is going to tell us how many more plants we have than when we started. So we're going to start with a certain amount, and that area is going to tell us how many more plants we have. But then if I look at the area underneath the second species, I get this area here. And that's going to tell us how many more plants I have for that species. So if I want to know which population is larger, I essentially need to look at which one added more plants in that year. So which area is larger? Well, if we compare the 2 areas, the one under the species 1 line and the one under the species 2 line, the species 1 has more area because essentially the area that's shaded right here, but it also has this area that I just kind of looped through. So species 1 is going to have a larger population after year 1. Does that make sense? Is that how I spell species? Yeah. So since there's a larger area underneath of species 1 between 0 and 1, the population is going to grow more. And since, again, they started at the same value, that means that that's going to end up with more. Now, if we also want to compare essentially the second year, or essentially both years, we want to look at areas again. So if we look at the area of species 1, I have all of this area in here. So I have all of that area, which is going to tell me the total amount of population for species 1 between the first 2 years. And then for species 2, I have all of this area. This area. Here. You get the point, hopefully. Which one of those 2 areas is larger? The area under species 2. And if it's harder to see because I've been having to erase them and redraw them, notice that in the first area, the first year, sorry, species 2 kind of didn't have this area in here, but in the second year, it gains this area. So the amount of area that it gains between 1 and 2 outweighs the area that it didn't have between 0 to 1, if that makes any sense. So species 2 is going to have much more area underneath of the function between 0 and 2 than species 1. So species 2 would have a larger population after the second year. Does that make sense? So we're comparing, we're comparing areas here. So the area under species 2 between 0 and 2 would be larger than the area under species 1 from 0 to 2. Okay. And then we want to know how does the population of species 1, how much does the population of species 1 increase during the first 2 years? So essentially now we want to actually know that value of that integral. So this is going to be the tiniest bit tedious. We're going to use our counting box technique here. I think it's the one that'll fit best. You can use a Riemann sum if you really, really want to, but I think the counting box technique is going to be a bit better here. So we essentially want to know what is the area underneath of this species 1 curve between 0 and 2. So if I'm gonna start by finding all of the full boxes. So there's one here, second one here, third, fourth, fifth, sixth, 7th, 8th, 9th, 10th, 11th, 12th, 13th. So there's about 13 full boxes here. And now this is when I have to start kind of piecing them together. So if I look between these two right here, if I group those two together, that would be approximately another box. So I'm going to have a 14th box there. If I group these two together, that's approximately one more box. So that's going to be a 15th box. And then what's the only area I haven't considered yet? I haven't considered this piece here and this piece down in the bottom left. So that piece up in kind of the top right is almost one full box, and the one in the bottom left is almost half a box. So we can't really combine them together to just get one box. It would be more than that. So let's go ahead and let's just call this one up here a whole box. Let's just give it a little more than it has and just say it's approximately one box, which then adding in this area at the bottom left would get us up to a total of 16.5 boxes. Does that make sense? So again, remember with these box counting techniques and then piecing them together at the end, you don't have to be perfect. You don't have to have a perfect full box. Just get an estimate of a general idea of about how many boxes are underneath of there. But then remember, when we're doing this counting box technique, it's not just about counting the boxes and calling it a day. We then have to figure out kind of the amount of area in each box. Now these ones are a bit weird. So let me consider one box. So let me map out this one right here. Let me just point out this box right here. So if I want to figure out how much area is in each one of these boxes, the thing I need to notice is on the t-axis, to get from 0 to 1, there's 4 lines. So essentially each one of those lines is going to be essentially a quarter, 0.25. So this distance here would be 0.25. And then on my y-axis, to get from 1500 to 3000, which would be a distance of 1500, we did it in 2 pieces, right? Because we have a jump from that line to that line and then that line to that line. So each one of the lines on the y-axis would be worth 750. That looks really bad. There we go. It's a little better. So essentially, right, the area of each box would be whatever the heck 1/4 times 750 is. I'm not going to find it at that point. I'll just put it as part of my answer. But so we not only need to know that there's 16.5 boxes, but we need to know the area of each box. Questions, concerns on that? It's been a while since we've done the counting boxes too. Okay. So all of that to say that essentially, so we wanted to know the change in population. So we essentially wanted to calculate the integral from 0 to 1 of species 1. So I called that S of t. So we found that there were approximately 16.5 boxes, but each box has an area of whatever 1/4 times 750 is. So that was the area per box. And so if we multiply that together, so 16.5 times 0.25 times 750 is 3,093.75. So let's just say approximately 3,094 plants. So that means that in those first 2 years, the population of species 1 grew by 3,094 plants. That's not the total population because we don't know where we started at. We don't know if we started with 0 plants, with 1 million plants, with 2 plants. So we don't know the actual population, but we know that between when we started and the end of the second year, between 0 and 2, it's grown by 3,094 plants. Questions, concerns about that question at all? We'll wait a couple seconds in case people are still writing stuff down, and then if there are no questions, we'll move on to 5.5. All right. Okay. So 5.5 kind of goes back to the fundamental theorem of calculus for a minute. And let me even write up in this corner 5.5 in case anyone's looking at this later when you have your homework next week and want to figure out where 5.5 is. So say f of t is a rate of change for a quantity. Then the integral of f of t is a total change in quantity between a and b, which, you know, these two pieces grouped together, they're kind of separated by that sentence there. But those two pieces are the FTC, fundamental theorem of calculus. And the fact that it's the total change is kind of exactly what I was saying with that interpretation cookie cutter thing. It's a change in something from A to B. But essentially with this fundamental theorem of calculus statement, we can solve for either f of b or capital F of b or capital F of a. And this is going to be used a lot when an integral is too complicated to solve by hand. Now, in terms of some of these, so there are going to be some integrals that we can't calculate by hand. If you have a calculator that can do so, I'm probably not going to go through it today, but I'll go through it before your final. I can show you an online calculator that I don't hate and that I will actually allow you to use on your final, because it'll be one that only does what it should and not what it shouldn't. But I'll show you an online calculator that you can use to do the integrals for the final if you don't have a calculator that can do so, because your final, of course, is online because they're all online. All right. Anyway, and the reason that this is what you can do with this is because essentially if we start with the fundamental theorem of calculus, say I wanted to solve for f of b, I wanted to get f of b by itself. Well, then all I would have to do is I would have to take that f of a term and I would just have to add it over to the other side. And then I could get whatever f of b is. And that's kind of what 5.5 is about, is we're going to essentially be given an integral statement and, you know, some value of the function, the antiderivative, if you will, and we'll be asked to solve for another value. Now, what if instead you needed to find f of a? Well, that one is very similar. It's just that the algebra has an extra step. Because if you wanted to solve for f of a, there's a couple different ways you could do it, but I would personally still add f of a over to the other side first. But then to get f of a by itself, you would then have to subtract that integral statement over to the other side. Now, technically, if you really wanted to, you could memorize both of those forms. What I do is I just remember the fundamental theorem of calculus, and then I just do the little bit of algebra to get whatever piece I want. Because I think fundamental theorem of calculus is something that kind of should already be in your brain, or should eventually get in your brain if it's not there already. And memorizing those other two forms just seems tedious when sorry, my English is breaking. When you can just find them from the fundamental theorem of calculus. Anyway, so we're going to do a couple examples of that. So I'll wait like 2 seconds in case someone's still writing that down, especially because I zoomed in by accident. All right, so let's say a bacteria colony initially has a population of 14 million bacteria. So we're going to need that eventually. So we kind of underline that. Initially has a population of 14 million bacteria. Suppose that t hours later, the population is growing at a rate of f of t equals 2 to the t million bacteria per hour. Give a definite integral that represents the total change in the bacteria population during the time from t equals 0 to t equals 2. So we want an integral. So we want an integral. Since we're going between time equals 0 and 2, we're going from 0 to 2. With an integral, in general, it can get more complicated than this, but in terms of our class, the smaller number is always going to be on the bottom, if that was a piece of confusion for anyone. And then we want to integrate that rate. So we want to take the integrand to be 2 to the t. Now, this is what I mean by this is often used when the integrals are more complicated to do by hand. We don't have, there exists an antiderivative rule, but we don't know the antiderivative rule for that. So we actually couldn't do that by hand. But technically, in terms of what that question was asking, that's all it wanted. It just wanted the integral. But now we're going to go ahead and we're going to do something with it, because now it asks for the population at time t equals 2. Now notice the thing we're actually given, the function we're given is the population rate, the growth rate. So we don't want little f of 2. We essentially want the antiderivative at 2. So we want the antiderivative of that at 2. Well, since the integral essentially gives us an antiderivative, we can use that, and we can use the FTC. So we know that the integral from 0 to 2 is going to give us whatever the antiderivative of 2 minus the antiderivative at 0 is. Now again, we technically don't know the antiderivative, and for this type of problem, we don't need it. That's kind of the point. So what we want here is we want this big F of 2. So if I want to get that by itself, what I'd have to do is I'd have to add the F of 1 over to the other side. Sorry, F of 0 over to the other side, not F of 1. Now we would have to then calculate that integral in our calculator. So actually, let me pull up on here, just in case. Excuse me. So if you don't have a calculator that can do so, here's what you're going to do with it. You're going to be able to use Desmos. Oh, wait, there we go. Let me just do that one more time, just in case. So if you don't have a calculator that can do so, Desmos is a wonderful, wonderful online calculator that doesn't do anything it shouldn't do. So if you want to use, if you don't have a calculator that can do integrals, you'll want to use Desmos. And essentially what you do is you just type in int, and it magically turns into an integral symbol. And then you can just type in the function, and it tells you the value. That doesn't look right. Why does that not look right? Oh, Lord, that's because I did the wrong value in my other class. Whoopsie daisy. So the value that we have for this integral is this 4.328. Otherwise, of course, you can plug that into your calculator and get it that way. Oop, that's not the right thing. So we would get that that integral is equal to 4.328. Now the other thing is that we need to figure out what this big F of 0 is. Now, since that's the antiderivative of the population growth rate, that would be asking for the population at time 0. But again, we're actually given that in the original statement of the problem. So it says in the problem initially has a population of 14 million bacteria. So that actually means that capital F of 0 is 14. So we can replace that with 14 to finish the problem. So then 18.328 is equal to big F of 2. Does that make sense? So we essentially used the fundamental theorem of calculus. We were given F of 0 in the original statement of the problem, and we were able to find the integral either using our calculator or you can use Desmos now. And then we just had to add them together to get our answer. Okay. So let's look at another one. So say we're given the original function is x times e to the x squared. And we know that the antiderivative at 0 is 1/2, and we want to know what the antiderivative of 3 is. So here it's kind of stated slightly differently, but it's the same type of question. So one thing you need to notice when you're doing these types of questions is you always need to know one of the antiderivative values and then want one of the antiderivative values. And so essentially, if you're not given an integral, the integral you're going to form is between the number you know and the number you want. Or vice versa. The larger number always goes on top. But since we know 0 and want 3, those are going to be our bounds. The number you want and the number you have are always the bounds. And so then our integrand is going to be that function. Now this one, once we talk about 6,6 a little bit, this would technically be able to be done by hand, but we don't know how to do it by hand yet. But anyway, this would give us the antiderivative of 3 minus the antiderivative of 0. And again, we know the antiderivative at 0, we're given that value, so we can just go ahead and solve this. So if we bring the f of 0 over to the other side, we've essentially set it up to solve what we want. So if we plug this integral into our calculator or into Desmos, so we have the integral from 0 to 3 of x times e to the x squared. That is 4,051.0. I'm going to do 42. Let me take 3 decimal places. And then we're told that f of 0 is 1/2. I'm going to change that over to 0.5 so that I just have 2 decimals here. So then we just add those two together to get 4,051.542 as our final answer for f of 3. Questions, concerns on that? Okay. 20 minutes. Okay, cool. All right. So this process is also used a lot, especially in business calculus, in terms of cost, revenue, and profit functions. So remember that C prime, the derivative of cost, is marginal cost, and that C of 0 is the fixed cost. So essentially, if I have an integral from A to B of the marginal cost, using the fundamental theorem of calculus, that would be equal to the cost function at B minus the cost function at A. If we think about this in terms of like our interpretation idea, this is going to be the cost to increase production from A units to B units. the change in cost between A and B, and I just kind of rearranged the wording a little bit. So the total variable cost of producing B units. So remember the variable cost, we talked about that way back when. That's essentially the cost to make the next item. And so, nope, yep, sorry, nope, that's right. Yeah, the cost to make the next amount of items. So if we want to think about that in terms of an integral, so we've had a lot of ways to think about variable costs. It started way back when with the slope of a linear cost function, and we've come all the way up here. So if we want the variable cost and we have the marginal cost, we can find the variable cost of B units by taking the integral from 0 to B of the marginal cost. Therefore, if we want to know the total cost of producing B units, so the difference between the cost to make them and the total amount of cost. So remember, the total cost includes the fixed cost. So essentially this doesn't include fixed. And this total cost includes fixed. So remember, there is a difference between the two, between variable, the cost to produce, and then the total cost of producing. And this would be the essentially the fixed cost plus the variable cost, which is kind of how we presented it like way back when it came to linear functions. But here the fixed cost is going to be represented by just C of 0. And then the variable cost is going to be represented by this integral now. And this would give us the total cost of producing B units. So we've got one example of this, and then we're going to be done for the day. So if marginal cost is given in the graph below, so we're given marginal cost, and the fixed costs are $1,000. Find the total cost of producing 250 items. So we essentially want the cost of 250 items. Well, we're not given the actual cost function, and we're not even given the marginal cost function, so we can't find the antiderivative to just be able to find it generically. But we do have this new thing that we just wrote down, where this will be the cost at 0 plus the integral from 0 to 250 of the marginal cost. Now, C of 0, which would be the fixed cost, we're given. That's just 1,000. We're given that in the problem. So essentially the main point here is this, this integral value. Now that integral value we can find by essentially using this function, the graph that we're given, and we just need to find the area underneath of this graph. So at this point, we could find a Riemann sum and average the two. We would really want to average the two if we were doing Riemann sums here. So instead of Riemann sums, let's do another count the box. So let's go ahead and count the boxes underneath of this function between 0 and 250. So essentially all of the boxes underneath of that function. So I'm going to zoom in to make that a little better, a little easier to see maybe. So let's start by finding all of the full boxes. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and that's about all the full boxes there. So now we got to start kind of piecing them together. So if we take these two right here, this almost full box and then the little tiny piece next to it, that would give us about another 15th box, another box, so 15 boxes. If we group these two up here together, and maybe even that last little tiny piece up there, that'll give us about another box, so 16. And now the piecing gets a bit more complicated because they're not quite as nice. So let me take this one over here and this piece over here. I'm going to piece those together if you let me do it like that. It's going to give me another one, so I would say that's about a 17th box. Sorry, I'm just looking at something. Okay, cool. And then with the rest of these are almost one full box. So like between these last three, oh, and there's this piece here. So actually, hold on a minute. These two right here will get us about an 1/18 box. And then the last thing we have is essentially these two right here. Now those two are almost full boxes in and of themselves. So if we put them together, they're going to be a little less than 2 boxes. So let's just go ahead for our sanity and say that's another 1.5 boxes. So let's go ahead and say 19.5 between those two. So it essentially got me another 1.5 boxes. Is that okay? Oh, there's a little piece up here that I missed. It'll be all right. Let's just say 15.5. 19.5. Not 15, sorry. 19.5 boxes. Oops. So, zoom back in the tiniest bit. Oh, too much. So if we just found that there's approximately 19.5 boxes. Remember, to actually calculate the integral, we don't just care about the number of boxes, we need to care about the amount of stuff in each box. So each one of these boxes is a 50 by 2 box. So we need to take into consideration the area of each box, which is about 50 times 2, or 100. So if we find then that 19.5 times 50 times 2 tells us that there's approximately 1,950, it would be dollars here, represented underneath of that function. So we'd be able to replace that integral with 1950 to give us 2950. So we can say that the cost of producing 250 items is probably approximately $2,950. So even though we didn't know the full cost function, we don't even know the function for marginal cost, we were still able to estimate the total cost of producing those items by essentially manipulating the fundamental theorem of calculus to be able to solve for a value. So that's what 5.5 does. We're 10 minutes early, but A, I don't have the 6.6 notes up, and B, I don't think it's worth it to start it in 10 minutes. So we're just going to call it there. We are done, right? Yeah. So that's going to be the end for today. If you have any questions, feel free to stick around. So again, next Monday, we'll go over 6.6 a little bit, and then the Monday afterwards, we'll have a review session for your final. There will be one last homework assignment up next week. It'll be extended a little longer than a week to account for Thanksgiving. And yeah, we're almost done, guys. So if you have questions, feel free to stick around. Otherwise, have a great weekend. And I'll see you all on Monday. You do not